We are moving on in chapter 20. And remember, right now in chapter 20, we are studying nucleophilic addition reactions, where we are adding nucleophiles to the carbon-oxygen double bond of aldehydes and ketones. In the last set of material, we looked at oxygen nucleophiles. In 20.6, we are looking at nucleophiles that are nitrogens. And so again, these are going to be compounds where the atom that's attacking the carbonyl carbon is a nitrogen. And we're going to divide this up into two different types of nitrogen nucleophiles. We're going to start with primary amines, which is going to include ammonia, even though it's not technically a primary amine. So even though we've used the word primary to describe things before, like primary carbocations, primary carbon radicals, we've never used the term primary to describe an amine. An amine is, the amine functional group is a nitrogen. A primary amine is going to be a nitrogen that has one alkyl group and two hydrogens on it. Ammonia, as you know from Gen Chem, is just NH3. These compounds have lone pairs of electrons on the nitrogen. That's what makes them nucleophilic. We can also see this reaction work with a couple of other types of nitrogen nucleophiles. So we can have this guy. Even though it has oxygen with lone pairs on the oxygen, the nitrogen is still doing the attacking. And then we can also have this guy right here. So any four of these can serve as nucleophile for this particular reaction. The generic reaction, I'm going to draw it for acetone, but this also works for ketones. And I'm going to abbreviate the nitrogen nucleophile as RNH2, because if you look at all of the structures of these nucleophiles, they all have at least two hydrogens on the nucleophilic nitrogen. So I'm going to abbreviate it as RNH2, and this is an equilibrium reaction. And it's acid catalyzed, so I'm going to put H plus down on the bottom. And get ready for this. This makes carbon-nitrogen double bond with the R group from the nucleophile still attached. So this R group right here is either going to be a true R group if we're talking about a primary amine, or it's going to be a hydrogen if we were using ammonia, or it's going to be an OH or an NH2 if we were using one of these other types of nucleophiles. This molecule with a carbon-nitrogen double bond is called an imine. Not amine, imine. The acid catalyst that we use for this reaction, H+, your textbook likes to use TSOH. It also likes to use H2SO4. Whoa. SO4. Sapling likes to use HCl, and sapling likes to use H3O+, and you could use pretty much any acid you want. And this reaction is totally reversible, so we can convert the imine back to the aldehyde or ketone. When we do that, we still need an acid catalyst for the reverse process, and we're going to want it to be dilute. So we're going to put a little water in there as well. And this is just going to reform the original ketone or aldehyde, and it's also going to return to us whatever nitrogen nucleophile we used. So we're going to look at the mechanism for the forward reaction, first of all. And for this mechanism, we're going to use just a nice little aldehyde so it's easy to draw. And I'm going to use sulfuric acid as my acid catalyst. And I'm going to bring the nitrogen nucleophile in a later step. And this whole mechanism is in equilibrium, but just to make things easier, I'm just going to draw forward arrows the whole way through. But it is an equilibrium reaction. So the first thing that happens, and I'm going to sound like a nag, whenever you have an oxygen in the presence of an acid, the very first thing that you should always do is protonate the oxygen. So that's our first step. And then we end up with protonated aldehyde in this case. And so we've seen this before in our generic acidic condition, nucleophilic addition reaction. Now the carbonyl compound is ready for the nitrogen nucleophile, and I am going to pick a nice little nucleophile. I'm going to use just this little methylamine. The lone pair of electrons on the nitrogen are going to go after the carbonyl carbon and open up the carbon-oxygen double bond, and we are going to make, and again remember this is all in equilibrium, but I'm only drawing forward arrows. So we've put another pair of electrons on the oxygen. It doesn't have a charge anymore, and we've made a carbon-nitrogen bond. And that nitrogen still has all three groups attached to it, which means that with the fourth bond it made, now the nitrogen has a positive formal charge, which is no good. The deprotonated sulfuric acid, HSO4-, or whatever acid you used for this reaction, is going to come in, and it's going to grab one of the hydrogens off the nitrogen, break that nitrogen-hydrogen bond, and get rid of the positive formal charge on the nitrogen. So that's looking pretty good. Except now we have this problem in this last step. We recreated our acid. When we used HSO4- to grab that proton off the nitrogen, we recreated, in this case, H2SO4. And anytime you have an oxygen in the presence of an acid, that oxygen is going to get protonated. Now you might be asking yourself, why is the oxygen doing the protonation? Why isn't the nitrogen getting protonated instead? And the nitrogen is getting protonated. Some of the nitrogens are getting protonated. Notice that if we protonate the nitrogen, we're just returning back to the previous step. And this reaction is all in equilibrium. So protonation of the nitrogen does happen. It just backs us up in the mechanism. And we're only drawing steps that take us forward in the mechanism. So let's draw what we have now. We've got our nitrogen, the hydrogen and the methyl group on it. We have our oxygen, which has now got an extra hydrogen on it, and it has a positive formal charge on it as well. And to resolve that positive formal charge, you can see, I'm sure you can see where this is going. We have a water molecule that's a good leaving group, and it's ready to go. And it is going to come off of the molecule. When that water molecule leaves, the lone pair of electrons on the nitrogen come up, and this is where we get our carbon-nitrogen double bond and kick off the water. So we end up with, first I'm going to draw this really ugly carbon-nitrogen double bond upside down. And our nitrogen has a positive formal charge. And so I'm just going to redraw this so that it doesn't have weird bond angles. And that means now my nitrogen is sticking up instead of down, but don't let that freak you out. So last thing that we have to do is, you can see we have a positive formal charge on our nitrogen. So we've got to use something to take that proton off of the nitrogen. We have HSO4- that we can use. We can use pretty much anything to do this deprotonation. But for this mechanism, we'll use our conjugate base. And that leaves us with the imine product.